Hello, ni hao. My name is Lennart van den Berg, working at TNO, the Dutch Applied Research Organization, and I'm responsible for the Electrolyser Innovation Program. In the next 25 minutes, I want to discuss with you the following 5 topics: the Dutch hydrogen strategy, how TNO helps with acceleration of your innovations, next generation electrolyzer technology, what's the potential of offshore hydrogen production, and what's the effect of hydrogen being an indirect greenhouse gas. But let me first start with the following message. We need to accelerate. The CO2 levels in the atmosphere are rising and the effects are enormous. We're not on track to reaching the climate targets of Paris. More effort is needed. And as you can see, the consequences are big. Arctic sea levels Arctic ice is melting, and severe effect of area being burned, flooding, etc. So more effort is needed. And hydrogen will play an important role for decarbonizing the heavy industry and integrating huge amount of renewable electricity in our energy system. But more effort is needed. That's the main message here. What the Netherlands is doing in the area of hydrogen. The Dutch hydrogen strategy towards 2030. One of the important aspects of the Dutch hydrogen strategy is our own hydrogen production. Within the North Sea, we've got an enormous potential of offshore wind energy. At the moment, we are producing around 3 gigawatts, and we have plans, solid plans, up to 2030 to go to 21 gigawatt of installed capacity of offshore wind energy. And the potential is even bigger. Over 70 gigawatt of offshore wind we can deploy in the North Sea. And part of that wind will be converted to hydrogen using electrolysis. And the reason for that is we at a certain moment we're producing more offshore wind electricity than there is electricity demand. So we need this hydrogen to transform these electrons to molecules, because otherwise we can't use the full potential of the offshore wind capacity. So we see electrolyzer really as a technology which is enabling us to use much more of our offshore wind potential. The second part is the importing of hydrogen. We've got some of the big harbors in Rotterdam and Amsterdam and Groningen. And these harbors can play an important role of importing hydrogen or other energy carriers like ammonia or methanol to be used in the industry in the Netherlands or to be transported to Germany or Belgium. So this import of hydrogen will play an important role in the future as well. Thirdly, we have currently a natural gas pipeline, and there are solid plans in place to transport the natural gas pipeline into the hydrogen backbone, basically connecting the 5 clusters, industrial clusters in the Netherlands, and also connected to underground storage in salt caverns and even in empty gas fields. And the fourth aspect is aligned supply and demand. At the moment, the Netherlands is, after Germany, the biggest user of hydrogen, but this hydrogen is all gray hydrogen with high CO2 emission. And the idea is that part of this hydrogen, gray hydrogen, will be transformed to green hydrogen, actually all, and there will be new off-takers. For example, the steel industry, where we're going to replace coal by hydrogen using DRI technology. And the fifth is really a lot of enabling aspects. So scale-up schemes, regulation, and safety programs, because that's really important. Safety is absolutely #1 priority here. And the last 5 years, a tremendous amount of projects being executed in the Netherlands along the whole supply chain, from hydrogen production, storage, import, offshore hydrogen, transportation, and all different applications, from industry to mobility to some experience in the built environment. Now what we see, these projects moving from conceptual states now much more to pilot and realization. And what we also learned, there must be clarity on regulation, there need to be more safety standards in place, and collaboration is key. So if we want to accelerate the technology development and the learning curves, data sharing is really important, and share the learning from these projects. You can find all these projects online, clicking on the link under in this presentation. And last year, we launched the Dutch Hydrogen Roadmap with blocks up to 2025, 25 to 2030, and after 2030. And here concrete targets are given for our own hydrogen production, targets for import, targets when we want the infrastructure and storage capacity ready. And it's really an integrated approach. So because we need to develop a whole supply production chain from production up to different applications. And we're also looking at the different policy frameworks, safety, societal acceptance, and also the role the Dutch industry can play, the high-tech industry. Can we produce our own electrolyzers? Can we produce our own membranes? So this high-tech industry will also play an important role in the Netherlands. Another important aspect and main driver is regulation. I think Europe, and especially also the Netherlands, is taking a lead in this regulation to give the industry clarity from how much hydrogen do we need and clarity on the hydrogen offtake. You see here the Renewable Energy Directive, RED II. And in this RED II, there are clear targets about the percentage of hydrogen being used, for example, in industry, green hydrogen. There are now suggesting that in 2030, 50% of the hydrogen being used in industry need to be green. And if this become reality, this will result in an incredible demand of green hydrogen. At this moment, the Netherlands is using around 1.5 million tons of grey hydrogen. If half of that will be green, this causes a huge amount of green hydrogen. This needs to be deployed before 2030. So, and not only industry, there will be mandates for transport. There will be mandates for aviation by synthetic aviation fuels, sustainable aviation fuels. This will be important. And also for maritime shipping, there will be targets. And these targets are really give clarity to industry to move forward with their green hydrogen development plans. Let me give you some introduction to TNO. TNO is a not-for-profit organization owned by the government. Around 3,000 people working around different units. Myself, I'm working in the unit Energy Transition and Materials. We are based in the Netherlands, but we have an international focus. If you're looking at our work in hydrogen, we are working around the whole supply chain of hydrogen. We're looking at starting with electricity production, wind turbines, solar. We're looking at electrolysis, but also production of hydrogen by biomass. We're looking how we can use the existing infrastructure by existing gas infrastructure using hydrogen. We have a big group of geologists looking at the underground, how we can optimize the use of the underground for carbon capture and storage, for heat storage, but also for hydrogen storage. And we look at different applications for hydrogen in the industry, steel industry, for example, in the aviation, producing synthetic fuels, and use of hydrogen in mobility, for example, in trucks and buses. And also important, the role of hydrogen in our energy system. Hydrogen is not a goal in itself. Hydrogen is really a means to an end, to decarbonize the heavy industry and to increase the use of renewable electricity in our energy system. And importantly to say, hydrogen is really connecting chemical industry with the energy sector, with the high-tech industry. So the amount of people working on hydrogen is growing every day. Here in this map, you see the locations, the number of locations where TNO is active in the Netherlands. Our hydrogen research is mainly in Petten, the north of the Netherlands, but also in Eindhoven, where we work on more on manufacturing technology. And we are based in the Netherlands, but really have an international focus. Especially for electrolyzer technology, we really see this as an international technology, and we need to work here with international companies, and we are doing that. This is our location in Eindhoven, the whole center, where we're working on high-tech manufacturing equipment. We're using that for solar cells, for batteries, for thin film electronics, wearables, but more and more also for the electrolyzer technology. We're using this called spatial atomic layer deposition to deposit ultra-low iridium loadings, for example, on the membrane or the PTL for in electrolyzer technology to reduce the iridium loadings. This is our location in Petten, the northwest in the Netherlands. And actually we built here 5 years ago one of the largest electrolyzer research labs in Europe. And in this facility, work on 4 technologies: alkaline, PEM, solid oxide, and anion exchange membrane. And for the ones who are not familiar with the electrolyzer technologies, you see here a picture with the level of maturity. As you know, alkaline is the most mature technology. Pilot plants are being built over centuries. The largest pilot plant is over 100 megawatts with multiple stacks. And you can see here, these stacks are enormous. The PEM technology, also mature technology. Systems are built in Europe and US of 20 megawatt plus. And here you see in this picture our own electrolyzer R&D stack, which is 250 kilowatt, and we can use for testing new materials, new membranes, new electrodes. The solid oxide electrolyzers, basically steam electrolysis, are operating above 400-500 degrees Celsius, where the others are low temperature electrolysis, typically around 70-80 degrees. A large system will be built in Rotterdam, 2.6 megawatt by Sunfire by next year. And the anion exchange membrane is still less mature. I mean, systems are being sold with small stacks. And this year, hopefully, there will be 1 megawatt stack electrolyzer operational consisting of multiple stacks. Where's TNO working on? Here you see our PEM electrolyzer innovation steps in our facility. So basically, we start with cell manufacturing, making our own catalyst-coated membranes. Then we tested them by rapid prototyping in our own developed test station from 1 square centimeters. And the most promising results we're testing on the largest station of 10 square centimeters single cell PEM electrolyzers. And after that, we go to a larger multiple cell stacks, 50 by 50, so 2,500 square centimeters. And actually, it's basically the last step before this technology can go to the market. And one of our important goals is typically this route takes 7 years to go from the lab towards industrial application. And our goal is to go much faster. So not in 7 years, but in 3 years, going from your first innovation on cell level to having this technology deployed safely in a full operation electrolyzer stack. The same we're doing for the solid oxide electrolyzer high temperature cell. We are making our own cells, own tape casting, own slurries, and we tested that in multiple electrolyzer test stations. And at the moment, we can make such a large cells by 30 by 30 centimeters. And as we know, this is one of the largest cells available at this moment. And one of the biggest challenges for solid oxide technology is obviously lifetime. How we can extend the lifetime and secure multi of 10,000 hours of operation. And another important challenge is the integration of the solid oxide electrolyzer technology in industry. Going to the third block, next generation electrolyzer technologies. Here we made a roadmap for the PEM electrolyzer technology. We see 3 different generations. Generation 1 is basically the technology being deployed currently in industry. Generation 2 is basically the same electrolyzer design, but new novel components. So thinner membranes, other catalyst materials, non-noble coatings, and obviously high volume manufacturing. If we're looking at the third generation electrolyzer technology, then we completely look at a new design, new electrolyzer architecture. So, example, membranes which are not using not fluoride membranes, or a non-noble electrolyzer catalyst. And as TNO, we are supporting companies in the first generation or with supporting with their pilots. Second generation, we work together with industry, integrating their novel components in our electrolyzer stack. And third generation, we really look at new innovation, breakthrough technology. And as you can imagine, it's quite a challenge. It's a trade-off, because on one side, we want to have efficient electrolyzer with a low capex and high durability. And that's quite challenging because we want to reduce the catalyst loadings, which have an effect on, if you go to a higher catalyst loadings, your efficiency going up, your durability going up, but your capex is going down. On the cell designs, if you go to thick membranes, it has a high good effect on your durability, but a negative effect on the efficiency. So we're actually not going to thick membranes, but we go to thin membranes from 100 micron, maybe even to 50 micron in a PEM electrolyzer. Same count for your operating conditions. If you go to a high temperature, your efficiency going up, but has an effect on your durability. So in that trade-off, we're working every day to improve the stacks. And what we see in the future, there will be stacks for different applications. So a different PEM electrolyzer for offshore application, different PEM electrolyzer, for example, at the steel industry with multiple of hundreds of megawatts, and different electrolyzer for offshore application connected to solar, because their operating conditions will be different. And obviously all these costs ending up with the total cost of hydrogen. And you see the efficiency is one of the most important parameters, because in the end, your electricity price is your main parameter in the cost of hydrogen. And one biggest challenges we see at this moment is harmonized test protocols. How can we predict the lifetime of electrolyzer cell stacks of complete systems? And at TNO, we developed what we called accelerated stress test protocols. So in this protocol, we can predict the lifetime by developing a protocol where we increase voltage, temperature in such a way that we can understand degradation mechanism, and there can predict the lifetime of an electrolyzer cell, end of life 10 or 20%. But this is at this moment, we're working with the industry and the Joint Research Center to get agreement on these protocols, because it's important that we get an industry-wide understanding of the protocols, standardized of an open stack, open test system. And here you can see some important stressors which cause degradation for the certain materials. So temperature, low current, on and off, which is obviously important when you connect to solar and wind. High voltage, low humidity. These are all stressors for the different electrolyzer components. And we are doing everyday work to understand the stressors more and see what's the effect is on the different key components. And other really important aspect is accelerator learnings. What we see in Europe, a lot of investments are done by government to support these electrolyzer pilots, but we see that much more learnings can be gained by sharing knowledge. So as TNO, we're going to connect our lab with labs with other research technology organization in Europe. We argue for clear quality standards of electrolyzer projects, and we argue to have more electrolyzer monitoring. And in Europe, we've got this trust database where 60 parameters of this electrolyzer ongoing projects are being monitored. And it's important to share these learnings to get much more understanding of large-scale electrolyzer in operation. And what are our expected cost reduction? Here we make an overview of the current electrolyzer cost, which is obviously depending on the cumulative installed electrolyzer capacity over a certain period. Typically now there's a PEM and alkaline is around 1.5 to 2 million per megawatt, and this cost will go down quickly, especially when we go to a high cumulative installed capacity. Another important aspect is the critical raw materials, especially in the PEM electrolyzer. If you're looking at the PEM electrolyzer, it's using iridium and platinum. And this material is really coming mainly from South Africa, Russia, and Zimbabwe. So can we reduce the loading of this catalyst material in the electrolyzer? And the answer is yes, we can. And basically, on the short term, this reduction of this catalyst loading is one of the most important strategies. Here you see different strategies for the PEM and alkaline electrolyzer. And obviously, substitution is really important to look at, but we don't see that this will have impact coming 5-10 years, because this technology is not mature enough, having reduction substitution for iridium platinum on the short term. Also, recycling is definitely important, but doesn't solve any problems coming 5 or 10 years. So we put quite some effort on reduction this iridium loading in the PEM electrolyzer. And luckily, we have some results there. By using this spatial atomic layer deposition, we are able to reduce the iridium loading by a factor of 200. Here in this table, you see the iridium catalyst in gram per kilowatt, and on the left you see the installed PEM electrolyzer capacity in gigawatt. And if you use current loadings, then we need 4.5 tons of iridium per year. And basically, that's nearly all the iridium which is being available globally. So then we are in the red zone. So the challenge is to heavily reduce your iridium loading as low as 0.01 gram per kilowatt by keeping the same performance. And now we're working with a group of industry to develop this technology further and to introduce that to the market. So that was on the technology development. Let's now go to the potential for offshore hydrogen production. Here you see the map of the Greater North Sea between the Netherlands, UK, Denmark, Norway. And the Greater North Sea has a huge potential of offshore wind, as I already mentioned. And in this scenario, we calculated what's the most cost-effective way of utilizing this offshore wind. And here we see that hydrogen will play an important role here. So if we're gonna deploy over 170 gigawatt of offshore wind, probably around 60 gigawatt of offshore electrolysis is needed in order to utilize all this wind energy. And this offshore electrolysis will be connected by existing or new pipelines to the Netherlands and Germany to be used in industry. And it's not only about infrastructure, it's also about underground storage. We did a study on the potential of offshore underground storage and onshore underground hydrogen storage. And actually, the Netherlands is quite suited with quite some potential of salt caverns and gas fields, empty gas fields which can be used for hydrogen production. And basically looking at 3 different applications: short cycle storage, seasonal storage, and strategic storage. And expected that we need multiple of these salt caverns or empty gas fields to comply with our future demand. Onshore storage is still much lower cost than offshore storage, but basically we gonna need them all. But still, it's under study for the offshore storage of hydrogen. If you're looking at cost projection in Europe, in this graph you see the levelized cost of electricity on the bottom and the levelized cost of hydrogen in the top. And if you look at where are the places with most low-cost hydrogen production, you see offshore wind is really in privilege, and especially Denmark and Netherlands has the highest potential, especially if the technology will be developed further for offshore wind and also the electrolyzer technology. And if you look for solar, which has much lower full load hours, a location like Portugal So the Southern Europe has the most potential with respect to lowest levelized cost of hydrogen production. If you look at offshore hydrogen production, there are different configurations, multiple concepts. Let me show you 4 concepts. One concept is the island configuration, having an artificial island with huge amount of hydrogen centralized production, which obviously requiring a huge investment. The second concept is a platform concept, using existing or probably new platforms to have electrolyzer being placed at multiple levels, which is an option. A third, maybe more even intelligent option is having an electrolyzer directly connected to the turbine, so-called in-turbine solution. And there, it's possible that this wind turbine not producing electricity anymore, but directly producing hydrogen with a hydrogen pipeline connected to a central location where compression is done to bring the hydrogen at a higher pressure to shore. And the interesting thing of this in-turbine solution, then we can save on power electronics, and you can utilize much more wind. But this requires also quite an investment of this wind turbine operators. So there's really a pathway which is still need to be chosen by the industry. And the third concept is more floating concept. So these are possible 4 concepts: island, platform, in-turbine, or floating, how this offshore hydrogen production can look at. But still, there are a number of challenges. Obviously, one of the known challenges is a harsh environment, producing hydrogen offshore. Second is having an electrolyzer offshore. Probably need to be dedicated electrolyzer because you want to have a lower footprint. So less square centimeters, you want to have a lightweight system, a system with less maintenance, which is really important. The environmental impact is important. What are we doing with the heat and the brine if you're going to use desalinated seawater? Safety is an important aspect, especially if you're going to use hydrogen on a higher pressure. And obviously the fluctuating input, if you connect it directly to offshore wind, the electrolyzer will go on and off quite quickly. So how to deal with that? Or do we need to have solution with batteries, for example, in place? And obviously installation is important. If you go to offshore, quick installation is definitely important. Going to my last topic, and maybe a new topic for most of you. That's the fact that hydrogen is an indirect greenhouse gas. Hydrogen causes, if you leak hydrogen in the air, it has a result that the methane will stay longer. And actually, methane is one of the strongest greenhouse gases, as we know. And this picture, you see an overview of the hydrogen in the atmosphere. And obviously, the dominant source of indirect hydrogen emission is just naturally by oxidation reaction by different components in the atmosphere. Also, we have a main direct source of hydrogen emission, which is now being caused by fossil fuels. So that's currently what's happening. So the red numbers are source of hydrogen currently, and the green are natural sinks. So this is our current situation. Then about the greenhouse gas effect of hydrogen. Here you see the global warming potential within 2 years and 100 years. And if you look at the global warming potential of hydrogen, it's somewhere between 12 and 33. So meaning that 1 kilo of hydrogen is as strong as is similar to 12 to 33 kilo of CO2 emission. And what does it mean? So it's really depending on your leakage rates. So if you leak 1% of 1 kilogram of hydrogen, this means that your footprint will be somewhere between 0.12 or 0.3 kilo CO2 per kilogram of hydrogen. But if your leakage rate is much more, so over 10%, your CO2 footprint of hydrogen will be somewhere between 1.2 and 3.3 kilo CO2 in the atmosphere. So that's really important to take this into consideration. So to be aware that hydrogen is an indirect greenhouse gas, because it's basically extending the lifetime of methane in the air. Important is that we are monitoring the hydrogen emissions at these pilot projects, and not only in production, but the hydrogen emission from production in infrastructure, potential import to hydrogen end use, to measure the hydrogen emission over the whole chain. Because it's still unsure what will be the leakage. This is another table which calculate from what's the potential leakage. Some say the leakage will be less than 1%. That will be the most hopeful scenario, but some say the leakage can be over 10%. And here you see the effect of what's the leakage of 10%, and then you come to huge amount of numbers of hydrogen when we have the hydrogen economy at full scale. And there's some difficulties because at this moment we are not able to monitor low volumes, measure low volumes hydrogen emission. So we need better measure equipment. We need monitoring programs. So to better estimate from what will be the hydrogen leakage rates we can expect. Will be that lower than 1% or even higher than 10%. We currently don't know. So this should be a global effort to monitoring the hydrogen emission to have better estimates about what will be the effect on this. Coming to the end of my presentation, as a summary, the Dutch hydrogen strategy, the Netherlands is one of the European front runners on hydrogen development across the whole value chain, where we can leverage the potential of offshore wind of the North Sea. How TNO can accelerate your innovation? We are an independent organization and working with industry to accelerate the technology development. Our goal is really create impact. We work on next generation electrolyzer technology, mainly PEM, solid oxide, anion exchange membranes, and solving one of the big critical challenges and doing that much faster. Not 7 years, but go to the market within 3 years with our innovation. Offshore hydrogen will be deployed in the Netherlands. We have the first pilots already this year or early next year operational, and will probably take an important role to utilize all offshore wind electricity we have in the Netherlands. And fifth point, I'd like to ask the attention for hydrogen being an indirect greenhouse gas. And we really need to monitoring the leakage and come with solution to prevent any leakage as low as possible, and to better estimate what will be the effect. Here I come to the end of my presentation. Thank you very much for your attention. If there are any questions, please reach out to me, and have a nice day further on. Thank you very much.